My name is Pierre-Yves Lajoie, and this video is about SLAM, a distributed, online, and outlier-resilient simultaneous localization and mapping system for robotic teams. This is a joint work from the MIS Lab of Polytechnique Montréal and the Spark Lab of MIT. In distributed visual SLAM, multiple robots share their visual data to build a common understanding of their environment. SLAM offers a practical solution to localize teams of robots without relying on an external positioning system and with minimal information exchange. We released the source code and Docker images for an easy reuse of the system components by the community. So first, what is the Multirobot SLAM problem? Here is a simple example with two robots without any initial guess of their relative position. Both of them are performing SLAM on its own to estimate its trajectory in the local coordinate frame. Then, when they meet each other, they can communicate with the neighboring robots and compare the past observation. This way, each robot can optimize its own trajectory given the new information to improve its localization accuracy in the global reference frame. One of the main issues with Multirobot SLAM is to detect valid inter-robot loop closures in presence of perceptual aliasing. This phenomenon occurs when two places are confused as the same one by the robots. As you can see on those pictures of 4 different places, distinguishing them is not always an easy task. So if we start again with our two-robot example, we can see that while adding an accurate loop closures allows us to recover the correct trajectory estimates, the presence of outliers due to perceptual aliasing will distort the results. This is the system overview of SLAM. Each robot runs 4 modules: a stereo visual odometry module for motion estimation, a distributed inter-robot loop closure detection mechanism based on peer-to-peer communication that does not require full connectivity among the robots, a distributed outlier rejection mechanism to mitigate the effects of perceptual aliasing, and a distributed post-graph optimization module using the measurements produced by the other modules. This makes SLAM a complete multirobot SLAM system suited for field experiments. The first key module of SLAM is the distributed loop closure detection mechanism that occurs during a rendezvous between two robots. As you can see, the robots share net-VLAP descriptors to perform place recognition. Then they share visual features for geometric verification. And then the resulting loop closures are fed into the outlier rejection mechanism. The second key module is the distributed outlier rejection mechanism based on the pairwise consistency maximization technique introduced by Mangasson et al., of which we propose a fully distributed implementation. Let's say we have two robots with a mix of valid and invalid loop closures. We first make the assumption that valid loop closures are pairwise consistent. This means that if we compose around the loop, we should end up with the identity in the noiseless case. In presence of noise, we need to set a threshold. Then, we search for the largest set of mutually pairwise consistent inter-robot loop closures. This distributed outlier rejection mechanism comes with no additional cost, because the pieces of information required already need to be shared for the distributed post-graph optimization that follows. Now, let's look at some experimental results. In this first case, we use two robots that perform independent trajectories, of which we see the top view in blue and red. Then, we use a SLAM system to align and correct the trajectory estimates. We first tried without the outlier rejection mechanism, and as you can see, it results in totally distorted trajectory estimates. The perceptual aliasing problem is clearly visible, since the result is nowhere close to the GPS ground truth. Then, if we tried with the outlier rejection mechanism, we can see that the resulting trajectory estimates are much closer to the GPS ground truth in green. As I mentioned before, in presence of noisy measurements, we need to set a consistency threshold for the outlier rejection. To look at the effect of this value, we ran SLAM in a multirobot simulator. From the first plot, we can observe that a larger threshold does not reject all the problematic outliers. But we can also observe that setting a smaller threshold has the drawback of rejecting valid measurements. From the second plot, we can see that the average translation error grows when we do not reject the outliers successfully. In our next set of experiments, we look at the effect of parameter tuning in the front end. On the x-axis, we look at two parameters that are usually fine-tuned to avoid the production of outliers. Then, on the y-axis, we look at the number of inter-robot loop closures that our system accepts in green and the number of measurements that it rejects in red. We can see that with the very conservative tuning of the front-end parameters, we get just a few measurements, but they are all valid. However, with a less conservative tuning, we get many more measurements, and even though most of them are rejected, we gain some new valid measurements. This ability to work in a less conservative setup is another benefit of SLAM. We also performed online experiments with SLAM. For those field experiments, we used two DJI Matrix 100, each equipped with the NVIDIA Jetson TX2 and an Intel RealSense D435. Here is a top view of our online experiments. You can see the two drones flying simultaneously and the resulting estimates in the bottom right corner. Our final set of experiments was done using a LiDAR-based front-end and data from the DARPA Subterranean Challenge. Even in this quite different setup, we can see the positive effect of the distributed outlier rejection mechanism of SLAM on the map estimates. In conclusion, SLAM is a robust and data-efficient multi-robot SLAM system suited for field experiments. In future work, we would like to improve the resilience to communication failures. Thanks for watching. Bye.